In the previous video, we talked about algebra, sigma algebra, and some properties of measures. And in this new video, we're going to dive deeper into the idea of sigma algebra, and we're going to learn how can we generate sigma algebra from a collection of sets. Let's first review the definition of algebra and sigma algebra. The difference between algebra and sigma algebra is that when we define sigma algebra, we require this collection of sets to be closed with respect to Boolean operations on countable sets. However, in algebra, we only require the set is closed with respect to Boolean operation on finite sets. Okay, so is sigma algebra unique? To answer that question, let's think about some examples of sigma algebra. For instance, again, let's be consistent with our notations from last time. Let omega to be our sample space. And we can construct two types of sets easily. The first type, we call it F1, and there are only two subsets in this collection of sets. So the first type, F1, is very trivial. We have omega and its complement, so that in this set we satisfy the fact that the complement of each subset will still be contained in this collection of sets, and we call this a trivial sigma algebra. And we can also create a somewhat complicated space where we include all of the subsets of omega. In this case, we essentially have a power set, and it consists of all subsets of omega. And conceptually, it is going to be the richest sigma algebra ever. When we have a finite omega sample space, F2 is fully obtainable. All we need to do is find all subsets. However, in other case where our sample space omega is not finite, when it's uncountable, then we cannot list all elements in F2, and F2 will be too large to present anyway. But we need to find a sigma algebra that's not so trivial, but it's also, in some sense, presentable. One way to construct such a sigma algebra is applying the idea of decomposition. We're splitting the sample space into disjoint sets. So we can write omega as d1 plus d2 all the way to dn. And one thing we need to make sure is that we want a countable decomposition, so we are able to count all the subsets of omega. And as I said, there are going to be disjoint subsets, which means di intersect with dj is just going to be an empty set when you have I not equal to j. And after we decompose this omega, we can form algebra by finding the union of finite number of elements in that decomposition. So we can have d1 union d2, d1 union d2 union d3. So we find these finite number of union, and we put all of that sets into one collection of sets, and that is going to be a new way of generating algebra. Comparing this new algebra generated from decomposition countable sets to F2, which is directly generated by omega, we have a smaller set. smaller set. Then the natural question will be, is there a minimum sigma algebra? Well, the answer is yes. We have smallest sigma algebra. So here's the definition of smallest sigma algebra. For any collection of basis sets, let's call it theta. The smallest sigma algebra that contains all sets of theta is called the smallest sigma algebra generated by theta. And we can use this sigma function to denote the process of generating an algebra from a collection of sets. And another way to claim this smallest sigma algebra is to say, if we take the intersection of all sigma algebra that is contained in, here should be in theta, then that's going to be the smallest sigma algebra. In the definition of smallest sigma algebra, I introduced the idea of generating sigma algebra from a collection of sets. This idea is especially useful when we're dealing with uncountable sample space. We're no longer able to brute force out all the possible union for an uncountable space. That's why we want to introduce the idea of basis sets, and we can generate a sigma algebra for the original uncountable sample space from a countable basis sets. So let's look at an example of how to generate sigma algebra. Imagine we have a sample space that happens to be the real line. And we know that the real line is uncountable. There are infinitely many elements in the real line. Because it's an uncountable set, so ideally we want to find subsets of this real line and generate sigma algebra from the subsets. So if we look at a set of intervals where it's half open, half closed, and A is always less than B, and A and B, they are on the real line, and let B to be the system of subsets of R, which are the finite sums of disjoint intervals from the form A and B. So we define a new interval A as the sum of finite disjoint intervals. When I say disjoint, I mean that AI, BI, and AJ, BJ has no intersection when I is not equal to J. In this new collection of sets, is this an algebra already? Well, it is not an algebra because it doesn't satisfy the three criteria. For example, if we have a set A that has the following form: 0, 1 minus 1 over n, and of course it belongs to the set B. But if we take a countable union of such intervals, so union of an, where n from 1 to infinity, actually gonna give us an open interval of 0 and 1 because we're approaching here, because the maximum number you get here is 1 minus 1 over infinity, and that's can be think of as an open endpoint for 0, 1 open interval. And of course, this 0, 1 open interval is not part of the collection of sets we just created, since it's open on the right hand side and all the subsets in B has a closed right endpoint. So that's why we say that this union, this countable union, is not an element of the set B. So this set B is not really a sigma algebra. But can we generate a sigma algebra from this subset B? Example, if we take countable union of the subsets of B, which has this form where we have open on A and a closed endpoint on the right-hand side, and we want to make sure that A is less than B. If we do this union, as I've shown above, we're going to get a doubly open interval where both AN and BN are open. And then, can we get a closed interval out of this? For example, if we take an intersection of such interval, A minus 1 over N and B, as we are approaching the left endpoint A from the left, when we take this intersection at the end, we are going to get, as we are deviating from the left endpoint A, we're getting further away from left-hand endpoint A. The intersection of all such subsets are going to be A, B. So we can also get a closed interval from subsets of B. Can we get any singletons, which means only one element in the subset? If we take the intersection, the countable intersection of A minus 1 over N and A, we're deviating from A, so we're getting further away from A, and if we take intersection of all such subset, we will only obtain one single element, that's A. Apply the similar idea of using union, intersection, and complement, we can actually obtain different forms, except in addition to open, close, and singletons, we will have some unbounded intervals in these forms. So these new sets they form a new algebra. And let's step back a little bit. Remember, our original sample space is R. And if we want to construct a sigma algebra on R, which means for any subsets of R, we can do any countable union, countable intersection, and complement, and we will always get result that's still contained in R. What are the different possibilities of sum of sets in R and union of sets in R? You see that these 6 possibilities cover all the possibility of Boolean operation result on the space of R. So in summary, we successfully generated a sigma algebra space for the sample space R from this space B, which is actually a system of subsets of R. Instead of directly generating a sigma algebra from an uncountable space R, we first define a new subset B, a new system of subsets B, and then we generate sigma algebra from this countable subset B. And this way of generating subsets has a name, and the new sigma algebra generated from B actually has a name. It's called borel algebra. The subsets in the borel algebra are called borel sets. An important fact is that the borel sets are actually the smallest sigma algebra for the real line.